Oh, just put seriously that back. Oh. Man. Oh. Well, we're nearly there. Welcome back, everyone. Just run the clock and get started. And it's official. Looks like we can get started. Well, congratulations, we got through the first exam. Looks like a lot of people finished this one pretty quickly. It wasn't meant to be a really long exam, working down to the very last minute. As far as the grading goes on this exam, I'll have it completed probably around tomorrow afternoon. So I'll have the hard copies returned to you in class when you come back next time. So this is pretty much how all of our work is going to go through Canvas. We'll have our normal week when we come back on week 6, another normal week on week 7. Midterms week is going to be kind of a normal week for us as well. We'll have an opportunity to ask review questions on Thursday of this week ahead of exam 2. But also that means kind of repeating the pattern we did going into exam 1. Week 7 becomes pivotal. That's when we're going to know the definite coverage on exam 2 content. So if you're into seeing these problems early, I'll have the definite sections, the same kind of review guides that we've seen before on our upcoming exam 2. So essentially everything on the Canvas page is just going to repeat as a cycle, just like you saw from week 1 going into week 5. Other things we've got going on are our quiz 3 is going to be due tomorrow. Some people did this early, so if you did, good on you. You're already done on that one. And I'll have the quiz 4 posted down here below. But any questions at the moment, folks? Okay, well, we left off kind of a rough situation. We left off our chapter 4 material before exam 1 on Thursday. Then we had a weekend, we had an entire exam, and then now we're going back to it. So let's review what we did before getting through all that exam information. We were dealing with the 1.5 IQR rule of thumb and learning how to construct a box plot. In fact, we were about to do our very first one. We ended at this problem here mainly because these are some of the ideas that did show up on exam 1. So let's review the context to kind of warm up what we are even dealing with on this one. This example 2 came from the Cornell Lab of Ornithology, which holds the annual Christmas bird count, in which bird watchers all over the country at various locations, it says, I'm assuming probably universities, see how many different species of birds that they can spot. So looking at the data, if you just select one observation, this means somewhere in the country, there was a Christmas party and they found 128 bird species. Seems like a wild party. Then first thing we want to do was construct a box plot to get a better feel for these data. Sure, we could put this into the histogram, but the box plot itself has a really special role in descriptive statistics. So to construct that box plot, step 1, we had to import the data and get the 5-number summary out. I'm not sure if that data is still in the calculator, but we got the main things that we needed at least. Step 2 now is really just looking through the IQR 1.5 IQR rule of thumb. So this is our step 2, essentially, check for outliers. Reason we're doing this is we want to have the outliers reflected on the actual box plot when we go to construct it. So within step 2, if we're using the 1.5 IQR rule of thumb, this is the first step that we would take in that process. We have to know the IQR itself. It came out to us 34.5 bird species. And so now here's where we're going to do this upper boundary and then the lower boundary to see if we find any outliers whatsoever. Any questions at the moment with where we left off, where we're about to start? Okay, let's give this a try. Still within step 2, it's just a big step, checking for outliers. We're going to check the upper end, which means we're just evaluating the formula. Good strategy here is just to copy it down directly so that we know where everything goes. It helps us memorize the formula. So we'll go quartile 3 plus 1.5 times 1.5 IQR. So substituting that information in, the IQR is going to be the 34.5 calculated. Quartile 3, we'll see our 5-number summary on the left. So we'll put in 132 first, plus 1.5 times, then drop in the 34.5 for IQR, and we'll get a number out. What we want to do is, when we get this number, just like on the prior example on these notes, look at the data. Maybe look at the 5-number summary as well. Any number that's going to exceed this value is going to be flagged as a potential outlier through this rule of thumb. So now at this point, it's all about just jamming it into the calculator. We'll go 132 plus, pretty much just typing it verbatim, 1.5. Then if you're typing it verbatim, you can use parentheses if you like to indicate multiplication, 34.5, or just hit the multiply key for a little bit shorter of a process. And this is what we get, 183.75 species. Seems like a real number because you can't have 0.75 of a bird species. But just like these numbers here, decimals are allowed. These are just boundary points. This was for the 25th percentile cutoff. And this is just a boundary point for our particular rule of thumb, 183.75 species. After computing that, we pause, and now we look at the data. Would you all say we do have an outlier or no outliers on the upper end? Yeah, good call. The 184 alone, right, the maximum, exceeds this just by a little bit, 1/4 of a species. That's the only number that exceeds it. 166 doesn't quite get there. So like we mentioned, this looks like a pretty huge number just looking at the data. It's kind of neat to see it's also flagged by the IQR rule of thumb as being suspicious. So we'll say here, to finish off our work on the upper end, one outlier, and it was the 184, the maximum. Then we have to do it all over again. But any questions at the moment to this stage? Okay, there could have been no outliers like on the last problem. There could have been many outliers. If this came out as, say, 140, we would have flagged 150, 166, and 184 as all outliers. But for this particular data set, it's just that unique observation. So then after doing that, we just rinse and repeat, do it all over again. Now for the lower end. We mentioned there's a great way to think about this one. Essentially, you're just redoing this formula. If you're talking about the lower end, you go to the lower quartile, change from quartile 3 to quartile 1. Instead of adding on the lower end, you do the opposite thing and subtract. And then the rest is the same, 1.5 times 1.5 IQR. Then just another set of substitutions. We mentioned most of math, and the formulas that we're going to use is just going to be a whole bunch of substitutions, it feels like. For quartile 1, C on the left, we calculate that to be the 97.5. Then go minus 1.5 times. In place of the IQR symbol, we're throwing in 34.5. But everything in black and yellow highlighting, of course, as well, is just a repeat from the formula above. So all that changes is the 132 plus versus the 975 minus. So back in the calculator, let's go 97.5, now minus 1.5. It's a little faster to just go times instead of putting it verbatim like on paper. 34.5. And that's our lower boundary, 45.75 species. Let me try to fix some of that penmanship. There we go. So now that we have that number, we do like before. We check our data and see if we have any outliers on the lower end this time. Anyone see if we have any outliers, some or none? Some folks in class shaking their heads no, and yeah, I agree. It looks like no outliers in this case. It's really rapid. We may not even looked at the original data up here. You might have just been looking at the minimum. On the lower end, we flag an outlier by the 1.5 IQR rule of thumb if something is less than this cutoff point, 45.75. But the smallest is the minimum at 82 species, so nothing is below 45.75. Or it's easy to see on the data since the data is sorted. The minimum is 82. So we might just conclude by saying no outliers on the lower end. We don't want to say no outliers because it's good to say on the lower end. There was one outlier on the upper end here. So this one we'll have to pay attention to when we go to plot it, the 184. When we go to plot it on the box plot next. So the idea with the box plot is we're going to take all this information, the 5-number summary here, the information on outliers through the rule of thumb, and just write this all as one graph. But any questions at all, folks, from step 1, step 2? Okay, kind of well on our way with it. And really, this is finally the new part of the notes. We've already done the 5-number summary on the first example and the 1.5 IQR rule of thumb as well. Now, finally, we're doing the box plot. My steps are between part A and part B. So step 1 to the box plot was the 5-number summary. Step 2 was doing the 1.5 IQR rule of thumb. And finally, step 3 of constructing the box plot is just to put it all together. First thing that's a little bit weird is there's a couple competing ways you can put down the scale. You could go horizontally, or you could go vertically. It really just depends. It's all up to you. I think our author is more often going to go vertically, so we'll do a vertical one as well. If you put your scale horizontally, it's the same information, just presented in a different way. But in a real sense, the first thing we want to do is kind of like what we did all the way back in section 2.2. Once we see what the data looked like, and we were constructing the dot plot for the data set on this one, I think this one was kind of morbid data about number of violent crimes. We first wanted to know what the max and the min was. Let me hide that, there we go, so that we can contain all of the data. We want to do the same thing, consider our min and max, come up with a unit that makes sense. Maybe it's by ones, maybe it's 5s, 20s, just depends on the scale of the data, and set up a scale wide enough to capture everything, even an extreme outlier if it occurs. Only difference is our scale is vertical to match up with the rating a little bit better. So here's how I probably start this out. Here's our vertical scale going this way. We want to add a unit to the scale anytime we do that. In the last section, we added it by just saying number of violent crimes on the horizontal axis. This time, the data is about the number of bird species spotted. So we'll put it here, going vertically, number of bird species. Then we decide on a scale. We don't necessarily want to start at 0 because there's no data there. We want a scale that contains the data and not be too extraneous with nothing going on. So our minimum might be 80. I wouldn't want to make it like 85 or 90, for example, because that's above the data. So let's start off at 80. In our prior dot plot, we counted off by 5s, but that's going to take us a while to get 184. If we go by 10s, that might not be too bad, but that's a lot of tick marks as well. I'd say going by 20s might feel a little bit blunt, but that'd be pretty appropriate for these data. Again, it's all up to you. Go with what makes the most sense. Try to get everything to fit on your axes. Let's try by 20s. See how we feel about it. We'd be going up to 100. 120. The real challenge here is to try to make equal with tick marks, but do the best you can. 140. Here's 160 species. Then finally up here, 180 species. Well, not quite, right? We want to contain the data, so we should still go up a little bit further. Barely made my scale long enough to 200 species. Finally, this will contain everything, and our box plot is going to live somewhere out here. By the way, this is not always called just a box plot. Sometimes it's called a box. It's also known as a box and whiskers plot. Some people might have heard it said that way as well, and we'll explain what we mean by whiskers as we go to plot this. Well, so far it's kind of the same thing we would have done if we did a dot plot. It's just a vertical scale is the only thing that's new. And finally, we mentioned the box plot is just going to visually show the 5-number summary. So we're just pulling in this information now that we have our scale set. The box plot is just a brilliant way to say, where is, for example, the lower quartile? It's going to be at 97.5, and we draw it as a horizontal strip. Vertical if your plot is flipped. So 97.5, our scale isn't great, but that'd be just below 100. It's a little bit blunt because we didn't go by tens. So just put it in the right neighborhood and you'd get full credit. You don't have to plot this like a robot. So about there, that's meant to be just barely below 100. Looks pretty close, but I'll go with that. So that green line now just refers to lower quartile. Next thing we'll put down is the upper quartile, 132. Well, 130 would be here if we went by tens. So 132 is just slightly higher than that. About like that. This closes out the box of the so-called box plot. So now we've got a box. Well, could be a long rectangle depending on how long the interquartile range is. So it doesn't just show quartiles, it shows the distance, 34.5. In other words, the interquartile range. So that means variability is represented here. The wider that box, the more variable the data is, since that's the central 50% of all observations. It shows even more, the median, we can draw as a line segment. So that's inside the box. If our data is a little weird, the median could equal quartile 1, that's possible, or it could equal quartile 3. In that case, you're not going to see an inside line, but typically you would. Here ours is at 112, so just slightly above that distance there by the red dot. That's my best attempt at 112. Doesn't look perfect, but we'll go with it. So the center line means that's the median, the 50th percentile of all the data. And we'll also want to put the outlier and other information based on our box plot. But so far, this is how it goes together. The quartiles are represented this way. The median gets put into that position. And you don't have to put this on your notes. It'd be weird to add this as a legend every time you did a box plot, but just for a reference, that's the median value. Upper quartile is that value. And lower quartile is that value there. So we're just about done constructing it. Any questions at the moment? Okay, next thing we want to put in, while carefully considering the data, let's bring this table down, is the outlier. That's a good next spot to start in. That's the most interesting observation in the entire data set. We mentioned this was a Christmas party, so the outlier is not something that we disregard. It's something we investigate further. Again, maybe this was erroneous information. Maybe they got a little bit too celebratory happy and a bunch of people took the same picture of the same species. Maybe that value should really be like 130. But what the data says, an outlier of 184 is going to be plotted this way. This is 190, so 184 is going to be about there. And I'll go with a open circle to match the graphics on the next problem. You might go with a solid dot like this. Either way, it'd be conveying the same information. But that's where our outlier is going to live. And if we had multiple outliers, we would plot them as well. Not exactly like the dot plot. If I had a bunch of outliers right around 184, well, we'll just do our best we can by putting in more circles around there. We don't necessarily stack them like in the dot plot. But now we have an outlier put in. Next thing we want to put in is the minimum, 82 species. So here's the min. The way the minimum plots in is a little bit different now. This is the whiskers part of the box and whiskers plot, or just box plot for short. The minimum at 82 species comes down like this, a line segment that starts at quartile 1 and ends at where roughly 82 would be. So this is what we refer to as the whisker part of the box plot. And it's just a minimum value going in. Well, any questions about the minimum? Here's where you noticed it might get a little bit weird, right? Because 184 was both the maximum and the outlier at the same exact time. We don't do the same strategy. Once we find the outlier, it's as if we're partitioning it away from the data, and this one is the new max after excluding all, however many there might have been, just one in this data set, outliers. So in other words, the whiskers in the box plot aren't always the min and the maximum. They'll go to the smallest and largest observation in your data set after you tossed out the outliers of that data set. So 166 is that new value. That means we go up to this height. Let's see, 166 would be about up here. This would be 170. So it looks like I have it a little bit shy. That would be all right for a by hand sketch. So this value comes into that location right there. So we got it, folks. That's constructing the box plot. Kind of a lot of work doing it for the very first time. Any questions about what went on with the outlier? That's often, I'd say, the more confusing part about it. Okay, so next thing, probably the more challenging thing about all of this is we want to describe what we see in the box plot. We're mentioning at least 3 items, so it's specific. And we have to pull in the context of what's going on in the problem when we go to write this out. Let's maybe put this on a new page so we don't have a page break across that last part. And just as a reminder, here's the context. Okay, so the reminder of what's going on is we have a vertical axis, number of bird species. So these were the number of species spotted by the Christmas party people across these various 20 sites with the most species. Imagine though we didn't see this data here. Maybe all we had was the plot itself. In other words, we're not looking at the 5-number summary. Let's give just a rough description of what we see if we were just looking at it purely from the box plot right here. There's a lot of things you can say, so as long as you're bringing in the context and it's 3 true things you see about this display, it would qualify for a full credit problem on either a quiz or an exam situation. But what would you say is the biggest thing you'd want to mention? The thing that stands out the most, probably?
The actual max.
That one here?
Yeah, the real max, not that.
That one right there, yeah. I think that'd be worth mentioning. So looking into this data, we can mention this value right here. And then the way you said it is important too, right? It's the max if you didn't consider the outlier. So we might want to bring that in as well. So let's bring that in as maybe that would be two of the three items if we're really being careful counting these. You might say something along the lines of, keeping in mind the context, the maximum amount of bird species spotted was 166 when not considering the outlier, or you might say the suspected outlier, because we did use what is a glorified rule of thumb when not considering the outlier of 184 species. Let me try to spell species right. There we go. So that's one good thing you might say about this, maybe two, depending on how you're counting them. So we mentioned the unusual feature about the plot, the fact that there is pretty substantial outlier, maybe not the most extreme outlier out there. It was borderline, remember, when we looked at the rule of thumb. And this is what borderline looks like for an outlier by that rule of thumb. What else would you want to mention that you see on this box plot?
Would you have would it be safe to say that the average number of species spotted was roughly 130?
Yeah, absolutely. Instead of average, though, sorry, say again. Yeah, absolutely. We wouldn't say average because it's the median, but you're thinking along the right lines. We're thinking just the typical amount of species spotted, the central value, which is the median, and yeah, kind of hard to spot if we're just looking at the scale, right? That's kind of uncomfortable. If you were doing this as an exam question, all you had was a scale, you might have said maybe 110, 115. If you said 120, well, that's in the right ballpark. I don't think I'd be too punishing on that. Looks like it's pretty close by my eye. You could say approximately 120, and then now you're admitting you're just visually estimating. So any way along those lines would be a great statement. So we're mentioning the central value if we went this route, the typical amount of species spotted was approximately, let's go with approximately 120. The median value. So these are great responses because it's really telling us about the core feature of the data. Central value here would be the median, and it looks like it'd probably be a good way to represent the data as well, because you can get a sense of skew already. Remember that this is quartile 1 and this is quartile 3. This is 50% of all observations just from here to here. That means if we take another view of this, let's screenshot just this part right here, look at this really closely. If 50% of the observations are here, you might be able to say something about skew because 25% of the observations are just on this segment, and look how compressed it is. Data seems to be really accumulating quite a lot on this end, and the remaining 25%, including the outlier, is out here. That gives us a sense of skew. That might be your third thing you might mention. Or some people might mention, to go along with the central value, the typical amount, you might be saying something about the interquartile range. You might say 50% of observations go from approximately 100 species to approximately 130 species. That'd be a great thing to add. Let's add that in, approximately. Between 100 species. So that's this lower end. And up here, I think we're approximating as 130 species. Contains, sure, we could say 50% of the data set, and that'd be true. But more importantly, that's the central 50% of the entire data set. That's the middle group. And that gives us a sense of just how spread out things are, variability. So whereas the median is referring to the central value, mentioning the lower quartile and the upper quartile, you're essentially telling me what the interquartile range. We're talking about variability now. So let's say contains the central 50% of observations. And by this time, we've definitely hit 3 different items already. We have mentioned the unusual thing, the fact that there's an outlier, the central value, as well as this last line is telling us how spread out the data is, mentioning the quartiles. But let's suppose we were going for a fourth, just because maybe you had extra time on exam 2 and you just wanted to mention a fourth thing. Let's talk about skew. We might say during this Christmas party, the distribution of species spotted, or number of species spotted, is skewed to the, it's kind of tricky, right? Sure, there's an elongated end this way and a compressed end this way. So what skew would you say this is? Is this skew to the right or skew to the left? Feels unnatural unless you kind of turn your head. That can kind of help a little bit because everything has been rotated to vertical now. I agree. The numbers are going higher when it's starting to trail off. So that's right skew or positive skew, exactly. So if you decide to mention skew, we'd say that number distribution of species is skewed to the right. There's a lot of things you can determine just from a quick box plot. Histograms still have a really important role, and a dot plot was just a quick way to see where data falls without going through all the trouble by hand putting down a histogram. But this is one way to think about and interpret information from the box plot itself. Any questions at all, folks, with that new plot? Okay, we mentioned that this is a pretty big section in a certain sense. Sure, we came up with a new plot, but in all honesty, doing a plot like this is not too interesting compared to the histogram, unless just more is going on with our data. Say we have a big data set with more than one variable, a multivariate data set, then box plots can actually do a really great job showing us relationships between those variables. That's what we're going to take a look at now, next in the next problem. So here's our example 3. This example 3 also contains the data called, I think I have it on my thumb drive, FEV. You can find it on the Canvas page, this weird text document, fev.txt. We've done data before where it's been an Excel document, but I want to give you a feel for what a larger data set might really be formatted like. It'd be something like this one. So here's the FEV data. I can't tell you too much about what's going on here without the context, but here's what it looks like. It's a pretty large data set containing what looks like a lot of numeric information, except not all of this data is quantitative. Some of it is truly categorical. So now let's take a look at the context, see what's going on with the data. This problem is about the so-called forced expiratory volume, or FEV. We're told that FEV is how I'll call it from here on out, is a primary indicator of lung function and corresponds to the volume of air that can be forcibly blown out in the first second after a full inspiration. So usually these come with little devices, something that's going to measure that volume of air. And this is something that comes out of a medical setting potentially. Maybe you have some really gnarly pneumonia. The doctors want to see how bad it's impacted you. They want to measure how strong your lungs are at that given moment in the ER room. So they'll ask you to take a full breath. That's the full inspiration. Blow into the device and see how much air and volume is blown out. That's going to be the FEV in liters. So think of FEV as just a quick way to say how strong are the lungs. So this is part of the context. We know what the FEV stands for. In this column, lowercase instead of uppercase for no apparent reason. Now here's the context of the actual data set in full. The FEV.txt data file contains FEV values, so lung strength values, of a large sample of children, along with some categorical descriptions of each individual. So FEV, because it has units of liters, is quantitative. Now we're combining a quantitative variable with some categorical variable information. It's coded up in a strange way. This just happens to be convenient for statistical software. Smoke and sex are categorical variables in this data set. So that's the far right columns. It's a weird statement, right? We're told they're straight out categorical variables, even though we see numbers. But it's how these are used that tells us truly, are they categorical or quantitative? Here, the whole point of smoke is to designate whether the person in this data set, recall they're all children, so this is some interesting data for sure. 0 is going to denote the child was non-smoking, and 1 denotes the child was smoking. So this seems like it's some really pretty interesting data, some very serious real-world data. It's kind of comforting to see that zeros propagate a lot of the observations here in this data set. Loads and loads of zeros. You have to really look hard to find the ones. 1 means the child was smoking, but it might have been a designation for including secondhand smoke in the home or something along those lines. So it doesn't necessarily mean they were lighting up cigarettes entirely. But here's our first one in the data set. The column, if you remember above, was age. Then this was height. If I recall correctly, this is the FEV value. Or hang on, I think this one's the FEV value and this one's height in centimeters. We have a 1 for the smoking column, so that meant this child here did smoke, or maybe was exposed to secondhand smoke, they determined in the study. So that's what's going on with the smoke variable. And same kind of coding information for the sex variable. Using 0 and 1s, sure, they look numeric, but this is categorical. We're categorizing whether they smoked or not. For the sex column, we're just categorizing whether they're female versus male. So if we go to the top of the data set, just so we can see these descriptions, we select this row right here. This was a 6-year-old child with a lung strength of 1.6 liters for FEV, 53 centimeters high. This was a female that did not smoke. So that's what it's saying here on the data set. Well, that's the context. Pretty serious data, but sometimes that's what statistics wants to study, these kind of serious questions or contexts. And below is the histogram of that entire data set. Sort of, right? If you take a histogram of FEV, that means this is all the information you cared about. If this was all we used to study this data set and nothing else, that's not quite fair, right? I mean, smoking was definitely a big part of this. That's possibly why they're looking into lung strength in the whole first place. We're also ignoring the age data, the height data, and the sex data. But still, the histogram is informative, but it has its limitations, right? Nonetheless, let's say what we can say about this histogram, kind of as a review problem. The shape would be unimodal because there's just one made peak. It looks like just about everybody in this data set is accumulating, aggregating around maybe about 2.5 FEV. So here's our one peak. From that one peak, we would say that this is unimodal. Then when we're thinking about symmetry versus skew, it looks like it does have a kind of skew to it. Would you all agree? It's decently symmetric. If we ignored, say, this part of the data, if that was just gone, that's pretty symmetric looking data. But this gave it a slight skew to the right. It's not severe like we've seen in some of the other data sets, like income data, for example. But here, if you said roughly symmetric, I would say that qualifies for a response. I think a better response includes the skew. So let's say slightly skewed to the right. And based on our analysis of histograms that we've done in the past, would you say they're outliers based on what you see? Some of the class saying no. Do you all agree? Looks like we have a pretty strong agreement with that. And yeah, I agree. If there's a slight right skew, then a curve I'd put to this data would look like this. Here's what I expect to see. It's not unusual to see observations here. What's kind of interesting about this is if we use the 1.5 IQR rule of thumb, it probably would say these are potential outliers. So it's strictly just a rule of thumb. And sometimes when the data sets get large, things don't quite match up with what we would have said visually. I do agree with you. For a slight right skew, nothing's too unusual here, unless you saw observations that were like, say, even over here. Now we start to have unusual observations. That would be just a very, very strong child that probably could run a fast mile. But nothing too abnormal here. We'd probably say no apparent outliers. And that's a pretty strong statement, right? Because we have collapsed a really interesting study into nothing about the FEV. And this is the next thing that's pretty strange about outliers. Outliers visually checking just depend on how you see the data. And there's more than one way to look at this FEV data. We bring in box plots. That's a great way to look at this. So box plots really shine, not when you're looking at one variable alone. This was just practice for us, really. It shines when you start to split up a data set like this across a categorical variable. What are the interesting categorical variables? Probably sex. We could give a box plot for FEV for male versus female. That could be interesting. Most interesting of all would be potentially this one, right? Let's see how strong lung strength is when they did not smoke. That's the 0 versus when they did smoke. We would have box plots like these side by side, and we can see relationships in the data that way. Or why not age? We're going to go for age on our next graph that we are going to take a look at. But first, any questions with the histogram or any of the context at the moment? Okay, so if we took a quantitative variable and we decide to split it up across another quantitative variable, sometimes that's an unusual thing to do, but the fact that these ages are integer values, there's no 8.5, 8.21, not a bad approach to take. On the surface, this is a quantitative variable, but the end designation of whether you want to think of it as quantitative is sometimes just based on what you do with it. If I decide age 9 is a category, age 8 is a category, and so on, we could treat it like a categorical variable and do something like this display here. So now we have ages separating out all of these different box plots like we've just seen before. This is kind of a busy graph, so let's blow this up just a little bit and see what we can tell about it. So FEV goes vertically, kind of like how we had number of species going vertically. It feels a little bit odd at first because we're used to our quantitative variable going horizontally like this. But now vertical display, just so we can have the width of the page. That's one reason vertical is nice. And split up the FEV lung strength variable across all the ages. Some of them look a little bit weird, but remember, this is a 3-year-old and there's almost no 3-year-olds in this data set. Okay, found one. I think there's very few, and sometimes, remember, this is a 5-number summary for the 4-year-olds. You really need 5 pieces of data to show the actual whiskers up, above, and below. If you have 4 pieces, 3 pieces of the data, sometimes the software can do this to you, just kind of collapse it in. Or it's possible as well that the lower quartile here is also the minimum at the same exact time. That's why it didn't show up. But for one that looks a little bit more normal, say for the 4-year-old age group, just a reminder, this would be the minimum value. So the minimum lung strength amongst 4-year-olds is something like 0.75 FEV. This would be the median, or usually you just call that M. I think I'm remembering how the calculator writes it. M for median, or 50th percentile, is this observation here. Looks like I skipped one. Quartile 1 is the lower edge of that box. Quartile 3, much like the median, except it's the 75th percentile, is the upper edge. And this is the maximum. Also, there's no outliers for the 4-year-olds, 3-year-olds. But notice outliers do show up. 2 of them in the 6-year-old group, unless some of those circles are overlapped. You have to look at the data really closely. Looks like one here, a couple here, a few here. And that runs pretty counter to what we saw up here. In fact, sure, we said the 1.5 IQ rule of thumb probably might flag these as outliers, even though visually they don't seem like it. But this one is pretty far away, actually. This one might have looked like it's like 1 unit away in terms of the width of these rectangles from the main data on the histogram. So that one is actually pretty unusual, and so is this one up here. So again, this is the tricky thing about outliers. Whether you think you have any or not, sometimes just depends entirely on how you're visualizing the data. For data like these, which are pretty complicated, there was definitely a lot hidden here. Outliers showed up amongst certain age groups, the 6-year-olds, 10, 11, and 12-year-olds. Well, there's a lot of relationships we can see here. So that's kind of our job on part A, just to get used to this new way of looking at box plots as this overwhelming array of side-by-side displays. We want to ask and answer, what does the side-by-side box plot say about the FEV distribution that could not be discerned when we just looked at FEV alone? I guess we kind of spoiled it on one thing. We said outliers are now apparent, which were invisible in the histogram. And we can say so much more. Pretty much your creativity here is a big part of this on how you might want to answer this question. Let's take another look at this. Anything else that you would say is kind of striking that you'd want to mention now that you see this, which you never were able to see in the histogram above? Does anyone see any patterns, for example? Anything that seems to be an interesting pattern or something to do about centers or variability could be a good thought to add as well. Yeah, absolutely. That's definite pattern we see in the data. If we were to try to draw a line, which was to try to get to all the median values, it would look about like this. There's a shape of a curve that starts to accelerate around the 7, 8, 9-year-olds, and maybe taper off once we get into the 10, 11, 12-year-olds. Can't quite hit all of them and try to make a smooth line. Yeah, go ahead. Yeah, absolutely. That's just the major thing right away. Age was invisible here. We don't know how old these individuals are in this FEV from about 4.5 to 5. But here, that data is apparent. So let's take both of those kind of comments together. In the box plots, we can see the distributions for each age group and also see let's see how to say this without making it sound like a word salad. See how FEV increases as age increases. We're able to draw an interesting smooth curve through here. We might have tried to draw a straight line, maybe going like this, for example, but it does seem like it has some taper. Maybe a straight line doesn't model these data too well. And we definitely didn't want to try to draw a line that just zigzagged between all the heights. We're trying to get a smooth curve here when we're looking for those sort of patterns. So I think that's a pretty good response so far. Did anyone have anything that they wanted to include? Okay, I think other thoughts that could be worthy here, but we're running out of page space, but would be worth mentioning might have been, look at the actual widths of all these box plots. They're not just telling us about the central values, which we mentioned here, as FEV median values increase, but they're also telling us how variable things are. Not a lot of variability in 3-year-olds. They all have about the same lung strength. But come over here into the 17-year-olds, humongous variability. Central 50% for lung strength for the 17-year-olds takes a pretty large range, actually. These are pretty large as well. And this one has a big overall range from minimum to maximum. But 50% of the data is as spread out as possible on that one age group for 17. So you might have mentioned the 17-year-olds are the most, let me fix that pen right away, most variable. That's a kind of weird way to say it. Let's say the group, you could say with the most spread. Oftentimes our author says the group with the most variability or spread. That would have been worthy to mention as well. It's also curious to know that 17-year-olds had the highest median value, and then 18-year-olds and 19-year-olds went lower. This just could have been due to the random nature of the random selection of this data set, but it's pretty interesting to observe here. Something interesting going on with the 17-year-olds in terms of variability. Well, we also mentioned the outliers as well. That was the key feature that seemed invisible in the histogram. And so this is the important role of box plots on descriptive statistics, especially when you have multivariable data sets, categorical data, multiple categories for our variables, and multiple categorical variables at the same time, make these box plots really great for seeing these relationships. Let's take a look at one more side-by-side display. The data seemed less about how FEV changed with age, right? This is just more of us getting used to seeing these kind of displays. The study was more about how does smoking impact lung strength amongst children? Now, keep in mind, we did make one mention when we were in chapter 3, dealing with our contingency table or two-way tables, that to get at cause and effect, you really have to run an experiment, and sometimes experiments can't be run at all. At best, we can find our relationships, and relationships are tricky things as well. Here's another side-by-side display of box plots. Below, we have the categorical variable, smoke, versus the quantitative variable, FEV. A little bit easier to look at, but the more you look at it, the more disturbing it might seem at first. Recall, 0 is for non-smokers. So this is for the non-smoking. Lots of outliers on this one, which is unusual already on its own. 1 is for the one that were smokers. And it says, consider the display of the categorical variable, smoke versus quantitative variable FEV. Comment on this display using the context. Didn't say what to comment, so this is a pretty wide open question. But anyone see something very weird and maybe almost disturbing about this data set?
Smokers have a higher lung capacity.
Absolutely. Reading this, you would absolutely say, by this display, smokers have a higher lung capacity or lung strength. Absolutely. Here's how you could kind of tell. Look at the median bars. They're way different. Another way you can say this is we look at from here to here, that's 50% of all observations, because that's from the median line, the 50th percentile, to the top. So more than 50% of all observations have a higher lung strength than in this group. This is 50% of all observation as well. So if you're thinking in quartiles, the median down to the min, or quartile 1 down to the min, half the data set is below here, whereas half of the data set is above. Focusing on just the medians gives us the same kind of view. The median being higher, significantly higher, is telling us a lot about this. So let's say this right away. This is not an error in the data. The study was conducted soundly, and it's not an error in the graphics, how it was put together. Nonetheless, we're literally staring at a situation which says the children that, I don't necessarily want to say that smoked, because again, this might include secondhand smoking. So let's say it's the children that are in the smoking group. I don't know if this is any better, but let's go with that. The children that are in the smoking group have higher lung strength or lung capacity in terms of FEV, the forced expiratory volume, or the lung strength measurement. And that can't be right. There's got to be some explanation here, right? We know that smoking is not actually increasing your lung strength. So there's got to be a way to explain this. I don't see what makes this true, but is a good explanation of why we see this in the data. Is there any way to explain this statement, but say it's reasonable based off what we know is contained in our data? It's a weird looking statement, right? Saying people who are in the smoking group have a lot higher lung strength. What explains it? Makes it seem reasonable?
Probably that there's the number of smokers that's why the percentage is higher, right?
Not necessarily, but you're right. There is hardly any smokers in this data set. But I think what you're saying is right on the money. It's the age, right? The older the child, the bigger the lung strength, right? And that's what we were seeing in this graph right here. The older they get, the higher the lung strength they have. And at the same time, there might be another association here. The older the child, potentially, the more likely that they smoked in the first place. So here's a 12-year-old. One's here on the far right column that they smoked. Notice you're seeing loads of ones as you go to the bottom of this data set. There might be more ones than I thought initially. These 3 ones are 16, 16, 15-year-olds, and so on. Again, 15, 15, 16-year-olds. And at the top of the data set, the younger children, we're seeing just a whole load of zeros. But the age of the child is how big they are. There might be another way to explain this just by talking about the height, but that's associated with age as well. These variables are all highly interconnected, right? So the bigger the child, the bigger their lungs are just physically. So the larger their FEV value, yet they've had more chances to be placed in the smoking category, maybe through their friends or maybe at home and so on. Looking at the data, that seems to be a plausible statement, and that could be the explanation. So it's right here. There is a plausible association between the smoke variable and age variable. That explains what's going on here. The non-smokers are just younger, so their lung strength is lower on the chart. Let's say that in as few words as possible, but capturing the essence of it. Younger children are less likely to smoke and have a lower FEV value. We really have to justify that though, right? We really have to look at the data even closer to see if this is true. Younger children are less likely to smoke. Just scrolling through the data and saying that seems about right, it's not good enough. We need to do a little bit more with the data to justify it. But that's the exciting world of exploratory data analysis, like we're seeing here. Descriptive statistics can be done in lots of interesting ways. And also, these two outliers above here are probably things that we would not have realized are outliers if we were only looking at the histogram. These ones are kind of borderline, but the ones above stand out. These are the interesting kind of things we'll talk about when we talk a little bit more about experimental design. We absolutely cannot do any more about cause and effect with this kind of problem, but we think there really is a causal relationship that smoking can cause a lower FEV value. Yet, you have to explain these kind of graphics that can show up all the time. This is stuff that's associated with other weird paradoxes, like Simpson's paradox, for example, is another interesting way these kind of things can come up. But that concludes our whole section then, so far on dealing with the quantitative data, as according to box plots and more categorical variables. Any questions or last thoughts on this one? Okay, so now when you see a display that just doesn't seem to make sense, think about what extra variables there could be here. The variable age, smoking, and FEV are all kind of twisted together. There's confounding variables that are hiding how things are really associated, making us think things look wrong when they're really right. Or, I mean, worst case scenario with this problem is we might look at this and say, smoking causes higher FEV values. That'd be insane to write, but in a different context, that would be a danger when it's less obvious. So let's conclude this section. Chapter 4 now has the official due date of being on now, let's see, October 1st. Next, we're going to move into Chapter 5, where this one's going to be broken up a little bit more. In Chapter 5, we're going to start looking into quantitative data again, this time just one quantitative variable. Our objective is to model that variable, and for a preview of what's going on there, this is essentially what we're coming back to. When we looked at shapes of these histograms, sometimes just to determine skew versus symmetry, we literally drew a shape, something like this. What Chapter 5 is all about is actually drawing that shape and then modeling the data according to that curve. We'll later on call that the so-called normal distribution, but Chapter 5 has a lot going on with it, so here's how it really starts out. We're going to talk about a new thing, a new metric, or a new way to consider data in terms of its standard deviations. The z-score is going to be a computation that takes a data value, which we consider to be just y. Sometimes we call them y1, 2, 3, and so on. We subtract the mean, divide by the standard deviation s, and this is going to be the new object of study when we come back on our next class on Thursday. Essentially, what's going on with the z-score is it's going to measure how many standard deviations your data value y is away from its mean. So it's going to be a measure of how unusual things are. And this is some interesting data that I pulled off my computer last year. This 91 degrees seemed pretty unusual, and we can measure that. We can say how unusual by using z-scores itself. But probably not a lot of time to actually launch into this section just now. Any questions at the moment? Okay, well, I would like to introduce you all to Sam. Sam's been hanging out, taking a look at the course to see how things run. Say hello, Sam. This is the statistics class.
Hey, how's it going?
I think we're doing pretty good. This is a really late class, so if we look tired, then we probably are. Well, everyone, this is Sam. Sam is a course coordinator for Math 1153, all of the Math 1153s here at ISU. He's visiting us here today just to see how things run in this class, which is kind of cool. I don't tell a lot of people this, but this is the only second time anyone has dropped in my class to see what all goes on down here in Idaho Falls. So thanks for joining us, Sam.
You're welcome.
First right away because we didn't want to bias the data. This was you being candid, seeing how the class runs. If we introduce Sam right away, you know that's a bias right away. Things become less candid all of a sudden. But have a great night, folks. We're going to end class about 5 minutes early today. We'll be back here in 5.1 when we come back on Thursday. The other time I had a person join me for my class was in person. His name was Dr. Derryberry, and it was his real name, and he was the chair of the math department. And there's a cord back there on the laptop. At the very start of class, he tripped. So that was extremely stressful for me, being observed by a guy that just potentially injured himself, talking for 75 minutes. So that's why I just sort of hid the camera here so that I just could pretend that no one else is in the class in Zoom. Yeah, go
That's all
ahead.
good.
Yeah. Gotcha. So that's a good question. So find the conditional distribution of US opinions. So I think by negative, they might mean poor. Positive, they might be including good, excellent. And by middle, I think they're including just a category of only fair. So let me read that again, just to make sure that seems to make sense. Find the conditional distribution of the opinions of US adults, and the categories are combined into negative. So yeah, negative is just poor.
So it's just this again on negative?
I think this time they're including the don't know and NA from the categories. So they're throwing away some of the data. So yeah, it looks like it's going to be slightly the same, but maybe a slightly different value when you go to calculate it.
I'm so confused.
So when you got the, say, for poor 2.8%,
Okay,
you probably added the 326 and 29
Yeah.
together and then divided by the 2154
Yeah.
that was used.
yeah,
But this time it says, let's see, conditional distributions, negative poor, middle only fair, positive good excellent, do not include the values from DKNA.
so subtracting the 68 from it,
Yeah, we'll subtract 68 from the 2154
okay.
and then do that same division as before.
Oh, okay.
Super confusing though, I
That was
agree with you.
confusing, I was like, what? Thank you.
Yep, have a great night.